Upon successful completion of this, you should be able to define and calculate the electric potential of point charges, dipoles, and groups of point charges, define and calculate the potential due to a uniform field, define and calculate equipotential surfaces for charges and conductors, calculate the electric potential energy of groups of point charges. Okay, now this is equipotential surfaces in the electric field. Adjacent points that have the same electric potential form an equipotential surface. That's what equipotential means, which can be either imaginary surface or a real physical surface. The figure here shows a family of equipotential surfaces, that looks like these sheets of paper here, associated with the electric field due to some distribution of charges, which is not shown here. Okay, I blew this up so it's a little easier to see. Okay, path 1 goes from this point to this point on V1, on this equipotential surface. So no work is getting done here because delta V equals 0. Path 2 also goes from a point on one equipotential surface to another point on the same equipotential surface. So delta V for 2 is 0. Path 3 goes from V1 to V2. This one is not 0. This one also goes between V1 and V2. So that means the work for 3 is equal to the work for 4. So the work for 1 and work for 2 are both 0. Work for 3 is equal to the work for 4. Okay, so here's some examples of equipotential surfaces in electric fields. The electric fields are the blue lines with arrows on them. The equipotential surfaces are the dashed lines. So here's a uniform electric field, and what's a uniform electric field? Parallel plate capacitor. You have the positive plate over here, you have the negative plate over here. Okay, so the equipotential surfaces are parallel to the plates. Okay, and the electric field lines are perpendicular to equipotential surfaces and run from the positive plate to the negative plate. Here's a positive charged particle. The electric field, of course, is radially outward from the positive charged particle because positive particles are sources of electric field. The equipotential surfaces are perpendicular to the electric field lines and they form spheres centered on the positive charge. Here's a dipole electric field, which has a positive and a negative charge. The electric field lines begin on the positive charges and end on the negative charges. The equipotential surfaces are at right angles to the electric field lines. This is for Physics 222. If you are in calculus-based physics, the next couple slides are very important. This one. Now, if you are not in Physics 222, if you're in an algebra-based physics class, please skip ahead to slide 7. Which says Physics 122, and continue from there. So let's go back to this. Okay, so we have a group of field lines here. Okay, the electric field lines, so those are blue lines with the arrows on them. And we have a test charge that is moving from point I to point F along this path shown. And this is a non-uniform electric field. During a displacement ds, an electric force F equals Q naught E, where E is the magnitude of the electric field, will act on the test charge. This force points in the direction of the field line at the location of the test charge. So in other words, it's here. Okay, so the electric potential difference between 2 points I and F is Vf minus Vi equals minus the integral from I to F of E dot ds, where E and S are both vectors, when the integral is taken over any path connecting the points. Now, it doesn't matter what path it is because, remember, this is path independent. If the integration is difficult along any particular path, we can choose a different path along which the integration might be easier, as long as it's between the same 2 points. If we choose Vi equals 0, we can have, for a potential at a particular point, Vf equals minus the integral from I to F of E dot ds. In a uniform field of magnitude E, the change of potential from a higher equipotential surface to a lower one, separated by a distance delta x, it would be delta V equals minus E delta x, where E is the electric field, delta x is the distance, and this is a change in potential. Potential due to a uniform field, we're going to determine an expression for potential of a uniform field. And of course, here is our uniform field. Here are the potential lines. Okay, so field lines are these blue ones, and the path is from I to F here, between a higher potential and a lower potential. And here's the delta x, and here's the direction of the E field. Okay, so the electric potential difference between 2 points I and F is Vf minus Vi equals minus the integral from I to F of E dot ds, where E and S are both vectors. For a uniform field, E dot ds is E ds cosine 0, or EDS. E is constant, so we can pull it out in front of the integral. And we can integrate between the 2 points, and the length will then be just delta x. So for potential due to a uniform field is delta V equals minus E delta X. Now we're going to do the point charge. So here's our point charge, and we're going to take a point off some distance r away from the point charge. So we're going to determine an expression for the potential of a point charge. The electric potential difference between 2 points I and F is Vf minus Vi equals minus the integral from I to F of E dot ds. We're going to use a radial path. So Vf minus Vi equals minus the integral from r to infinity of E dot dr. The magnitude of the electric field at the site of the test charge is E equals kq over r squared, or the little r squared. We're going to set the reference point Vf equals 0 at infinity. And then we're going to say Vi equals V at point R. So then we have 0 minus V equals minus kq times the integral from r to infinity of 1 over r squared dr. We're going to solve for V, switch to R. V equals minus kq times the quantity 1 over r between the limits of integration between big R and infinity. And remembering that 1 over infinity is 0, we find that V equals kq over r. So the potential at any distance from a point charge is V equals kq over r. Now notice it's not an inverse square law anymore. It is now just an inverse. So this is a summary of the potential due to uniform fields and due to point charges. It's also for algebra-based physics students, physics 122 students. Okay, potential due to a uniform field, delta V equals minus E delta X. Potential at any distance from a point charge, V equals kq over r. A positively charged particle produces a positive potential. For a negative charge, the electric field line arrows would be reversed, and a negatively charged particle produces a negative potential. Now we're going to take groups of n charged particles, and we can apply the superposition rule and sum the potentials. And the lovely thing about this is potential is a scalar. So there's no directions or vector math to consider. So all we need to do is we know for one particle is just kq over r. We can pull the k outside the summation sign. So we can just V equals k times the sum of q over r for all the different particles. Signs, charge magnitudes, and distances are the only necessary consideration. Signs, the positive potential is for positive charges or negative potential for negative charges. So the figure shows 3 arrangements of 2 protons. Rank these in terms of the potential at point P from least to greatest. Well, if you do this, it turns out they're all the same. What you do is you apply kq over r for each of these particles in each of these different arrangements. When you do this, you're going to find out that V at point P is kq over d plus kq over big D for all 3 arrangements. Now, it doesn't matter what the arrangements are. All you need is the q's and the d's. Okay, we're going to determine the expression for the potential of a dipole. Here's a dipole. Remember, a dipole is equal and opposite charges placed a small distance d apart, and we're interested in the potential of some arbitrary point P off at a distance r from the charge pair. Now, r is very large compared to the separation distance between the charges. So the electric dipole potential is the sum of the electric potentials of a charged pair. V equals k times the quantity q over r plus a minus q over r minus. R plus is the distance between point P and the positive charge, and R minus is the distance between point P and the negative charge. We find a common denominator and combine. V equals kq times the quantity R minus minus an R plus divided by R minus times R plus. Now the distance between point P and the dipole center approaches infinity for distances R much greater than D. And for most dipoles, that's true because D is very small. So then the limit as R goes to infinity of R minus minus R plus equals D cosine theta, where the angle here, theta, is the angle between R and the dipole axis, and the limit as R goes to infinity of R minus times R plus equals R squared, because all of these R's are pretty much the same distance. Then the electric potential of a dipole is V equals kq times D cosine theta over R squared, or K times little p cosine theta over R squared, where little p is defined as q times d, which is the dipole moment, not to be confused with point P, and q is the magnitude of each charge, r is the distance from the dipole, theta is the angle between the dipole axis and the direction of interest, and d is the separation distance between the dipole charges. So here we have a group of charges arranged in a square. So what is the electric potential at point P, located at the center of the square charged particles shown in the figure? D, which is the side of the square, is 1.3 meters. Q1 is positive 12 nanocoulombs. Q2 is negative 24 nanocoulombs. Q3 is positive 31 nanocoulombs. Q4 is positive 17 nanocoulombs, and there are 4 charges. Okay, so we write down everything you know, which we just had on the previous thing. I'm not going to repeat that. We need to know V at this point. The physics of this is a potential of a group of point charges, geometry, and some trig. So we can use V equals K. We pull the K outside. K times the sum of Qi over Ri, sum over all the charges. We use trig to determine R. And R would be the square root of A squared plus B squared, where A and B are each D over 2. We then solve, so R equals the square root of the quantity 1/2 D squared plus 1/2 D squared, and that will equal D over the square root of 2. B will then be K times the sum of Qi over Ri, and we plug everything in. We wind up with V equals K times the square root of 2 over D times the sum of all the charges. So now we can plug in numbers. So K, of course, is 8.99 times 10 to the 9 newton meter squared per coulomb squared. We have the square root of 2. D is the distance here, side of the square. That's 1.3 meters. And then we have all the charges, 12 nanocoulombs minus 24 nanocoulombs plus 31 nanocoulombs plus 17 nanocoulombs times the units conversion to get from nanocoulombs to coulombs. The answer is V equals 350 volts. If you repeated this for other points, other than P, you would wind up with a 350 volt equipotential line shown in the lower right-hand corner. Okay, now this is again a physics 222 calculus based only for this. And if you are not calculus based, you would go to slide number 19. So if you're algebra based, please go to, or in physics 122, please go to slide number 19. Okay, so for continuous charge distribution of charge over an extended object, the potential is found by dividing the distribution into charge elements at dq that can be treated as particles, and then summing the potential due to each element by integrating over the full distribution. In other words, we're just replacing the summations with an integral. Okay, so we're going to find the potential at a distance d from a straight line of charge of length L. Figure A has a thin conducting rod of length L and linear charge density of lambda. Lambda would be how coulombs per meter, be the units on that. As shown in figure B, there's a little element of dx, okay, of the rod has a differential charge of dq equals lambda dx. This element produces an electrical potential dV at point P in figure C, given by dV equals K dq over R, where R is this distance here between point P and the little element. And we substitute in, we find out that it equals K lambda dx over the square root of x squared plus d squared. We get that from the geometry of this, square root of the sum of the squares. Now we're going to integrate. So we're going to take V equals the integral of dV. We can pull the K and the lambda out because they're constants. And now we're going to integral over the length of the rod from 0 to L of the quantity 1 over the square root of dx squared plus d squared dx. And we've used substitution at u equals x over d and du dx equals 1 over d to simplify. So we're going to take this integral and we integrate. So then when we do that, we find that V equals K lambda times the natural log of this quantity, x plus the square root of x squared plus d squared divided by d between the limits of 0 to L. After a little bit of, or a lot of mathematical effort, we find that V equals K lambda times the natural log of this quantity, L plus the square root of L squared plus d squared divided by d. Okay, now we're going to do the same sort of thing, but for a charged disk. We're going to find an expression for the potential due to a charged disk for points along the axis of the disk. We're interested in point P that's up here, along the axis of the disk. We're going to consider a differential element dq consisting of a flat ring of radius r prime with a radial width dr prime with surface charge density sigma and charge magnitude of dq equals sigma 2 pi r prime dr prime, in which 2 pi r prime dr prime is the upper surface area of that ring. The contribution of this ring to the electric potential P is dV equals dq over r, or k sigma 2 pi times r prime divided by the square root of c squared plus r prime squared dr prime. We find the net potential of P by adding via integration the contributions of all the rings from r prime equals 0 to r prime equals r. So V equals the integral of dV, and we can pull out the 2 pi k and sigma because they're all constants, times the integral of from 0 to r of r prime over the square root of z squared plus r prime squared dr prime. We can integrate. When we do that, we find out that V equals 2 pi k sigma times the square root of z squared plus r prime squared between the limits of 0 and r. After a bit of math, V equals 2 pi k sigma times the quantity, the square root of z squared plus r squared minus z. Now that's for a disk and a distance z above the disk. Now we're going to talk about the electrical potential energy of a system of charged particles. The electrical potential energy of a system of charged particles is equal to the work needed to assemble the system with the particles initially at rest and infinitely distant from each other. So we're going to start with two particles. For two particles at a separation distance r, uf minus ui equals q1 times vf minus vi. For r equals infinity, rf would then, and rf equals r. So then ui equals 0, so uf is ui plus delta u. We're going to remember that V equals K Q2 over R, so VI will be 0. They're infinitely far apart, so they don't influence each other. And VF will be K times Q2 over R. So then we have the change in U, which is what it takes to assemble it, will be UF minus UI, and that will be Q1 times K Q2 over R, that's at VF, minus VI, which is 0. Why is it 0 at infinity? Because they aren't influencing each other. So then we find that the electrical potential energy of a system of charged particles is equal to the work needed to assemble the system with the particles initially at rest and infinitely distant from each other. U equals K Q1 Q2 over R. Since energy is a scalar, we can simply add the energies of the particles. This is why you definitely want to be dealing with energy instead of electric fields here. The total electrical potential energy of a system of charged particles is the algebraic sum of the potential energies for every pair of particles in the system. Here's an example. Potential energy of a system of 3 charged particles. 3 charged particles are held in fixed positions by invisible forces. What is the electric potential energy U of this system if D is 12 centimeters, Q1 equals positive Q, Q2 equals minus 4Q, Q3 equals positive 2Q, and Q equals 150 nanocoulombs? Now, the way you handle a problem like this is you take each pair individually and then add them all up. Okay, so we write down the knowns, which I'm not going to repeat here. We just talked about them for a minute, and we need to know what is U. The potential energy U of the system is equal to the work to assemble the system, bringing in each charge from an infinite distance. So the formula is U equals the sum of Uij, where Uij equals K Qi over R. We sum the potential energies from each pair of particles, taking care to count every pair only once in all the pairs. There are 1, 2, 3 pairs. So U12 is K Q1 Q2 over D. U13 is K Q1 Q3 over D. U23 is K Q2 Q3 over D. We sum them up and we can pull out the K over D because it's a common factor. So U equals KQ over D times the quantity Q1 Q2 plus Q1 Q3 plus Q2 Q3. Now we can start plugging numbers in. So we have U equals K over D times positive Q times a minus 4Q plus a positive Q times a positive 2Q plus a minus 4Q times a positive 2Q. When you condense this a little bit, it ends up being minus K times 10Q squared over D. Now we can put the numbers in. So that's minus 8.99 times 10 to the minus 9th Newton meter squared per Coulomb squared. We have 10 times our Q of 150 nanocoulombs squared divided by 0.12 meters for D. It ends up being minus 1.7 times 10 to the minus 2 joules, or 17 millijoules of work to assemble this group. We're going to assume for a minute that the electric field is at some angle theta with respect to an equipotential surface, where theta is not equal to 90 degrees. Point A and B lie along the surface, and charge Q is moved by the field from A to B along a path on the surface. We're going to assume, as I say, the E fields form some angle theta with the surface, where theta is not 90 degrees. Now, the work done by the field on a charge is work equals F delta R cosine theta. That equals Q times E delta R cosine theta, where this is theta. Delta R is the path. Q is the charge. But work which equals Q delta V equals 0 because delta V is 0 for an equipotential surface by definition. Because all points on the surface have the same potential by definition. And Q is not equal to 0, E is not equal to 0, delta R is not equal to 0. The only possibility is this cosine theta term has to equal 0. That means theta has to be 90 degrees. So the correct picture to this is as shown here. The electric field lines are always perpendicular to equipotential surfaces. So here's the potential of a charged isolated spherical conductor. The top figure is the voltage plot inside and outside of a charged spherical conductor with a radius of 1 meter. So here's the radius. The y-axis is the potential. The x-axis shows the distance from the center of the sphere. Inside the conductor, which is an isopotential surface, it is a constant. That's what isopotential means. Outside the conductor, it falls off as 1 over r, just like it does for a point charge. The bottom figure shows the electric field strength on the y-axis and the distance from the center of the sphere on the x-axis. And at this point, you can see that we have this is a zero electric field inside the conductor. And then as because the conductor is an isopotential surface, there's no electric field inside an isopotential surface. And outside the conductor, it falls off as 1 over r squared as it does for a point charge. So the charge will redistribute itself on the outside of the conductor. Like charges always repel, so they go to the surface in order to get as far away from each other as possible. So the entire conductor becomes an equipotential surface. It does not matter if there's a cavity inside the sphere or there's a net charge inside the cavity. For outside the sphere, where little r is less than big R, V will then equal kq over big R, and that will be a constant, and E will be 0. That, of course, is inside a charged conductor. So there's no electric field inside the charged conductor, and the charged conductor is an equipotential surface, so the V is constant. For at the surface of the sphere, where little r equals big R, V just equals kq over big R. For outside the sphere, where little r is greater than big R, V equals kq over little r, and E equals kq over little r squared, which is equivalent to the point charge q placed at the center of the sphere. That's the Shell theorem. Now, it is wise to enclose yourself in a hollow conducting body because it's an equipotential surface. Okay, so it's an equipotential surface. This hollow conducting body is called a Faraday cage. It's used to provide electrical shielding for people and sensitive electronics. All points inside the metal car at the same potential. Since it is putting your body across differences in potential that can kill you, you'll be safe if you stay in the car. Now, judging from the arc length here, I guess this is about 6 million volts. This whole car, including this guy inside of here, is all at 6 million volts. As long as he stays inside the car and doesn't touch anything that's grounded or at a different potential, he's fine. Because it's potential differences that kill you. And yes, you can touch the inside surfaces and sit on the seat, which has metal springs and a metal frame. Notice the arc across the tire. The idea that tires insulate you is pure bunk. Modern tires are actually made with steel belts and carbon. That allows them to be conductors, and they conduct charge. This allows the charge to drain off quickly. Some key concepts. Positive charges move naturally from an area of high potential toward low potential. Electric field points toward low potential. Negative charges move from low potential to high potential. Later, we'll usually reference potential to 0 at ground. Ground is an infinite sink or source of charges. Sometimes the potential is referenced to 0 at a point infinitely far away, as in dealing with point charges. So it sort of acts like the infinitely far away as ground. However, it is possible to reference it arbitrarily to make it easier to solve a problem, just as PEG was. V is a scalar, which makes it easier to use and add than E, which is a vector, so always use V if you potential instead of electric field if you can. If you graph V versus distance, the negative slope of the graph at any point equals the magnitude of the electric field at that. Okay, so equipotential surfaces and lines recap. All points on a line or surface are at the same potential V. That equipotential means equal potential. No work is required to move a charge on any path from one point on an equipotential line or surface to another point on the line or surface. An equipotential line or surface must always be perpendicular to the electric field at any point. Equipotential surfaces or lines are continuous and do not end. The surface of an isolated conductor is an equipotential surface, whether or not the conductor is in an external electric field. If this was not so, then the free electrons in the conductor would move until it was so. The E field is perpendicular to the surface of a conductor. Now, equipotential lines and surfaces are rather like, or equipotential lines are rather like the contour lines of a topographical map, or like the isobaric lines on a weather map. Where they are close together, delta V and E are large, so the change of potential is large and the electric field is large. Equipotentials have a similar shape as the surface near the conductor's surface and become more spherical at large distances. Electric field lines bunch up, are closely spaced near sharp points or edges of conductors because the charges bunch up there. Now, these are all electric field lines. The equipotential surfaces would be perpendicular to these electric field lines. So they would follow the contour of this object when you're close to the object. But as you get further and further away, they become more and more like a point charge at a large distance. Sphere 1 with radius r1 has a positive charge q. Sphere 2 with radius r2, which equals n times r1, is initially uncharged and is very far from sphere 1. Then the spheres are connected with a very thin wire that retains only negligible charge. What happens? Well, the first thing we do is write down the knowns and unknowns. Sphere 1 has a radius of r1, the initial charge is q. Sphere 2 has a radius of r2, and that radius equals n times r1. The initial charge is 0. We're going to assume that n is greater than 1. And we need to know q for each sphere, the E for each sphere, the surface charge density for each sphere. After the connection, it's physics, after the connection, the two conducting spheres form one equipotential surface. So V1 will equal V2 equals KQ1 divided by R1, and that also equals KQ2 divided by R2. The charge is conserved, so the total charge remains constant as it spreads out over the surfaces of both spheres. So the original charge Q equals Q1 plus Q2. Those are the charges after they've been connected. And then E equals KQ over R squared. We're going to find the charge ratio. So we use KQ1 divided by R1 equals KQ2 divided by R2. And R2 equals NR1. So therefore, Q2 equals NQ1, which for n greater than 1 means the bulk of the charge winds up on the larger sphere, which makes sense. There's more room for it to spread out there. Now we're going to find the surface charge density ratio, Q2 or Q1, and that will equal sigma 2 times 4 pi R2 squared divided by sigma 1, 4 pi R1 squared. Cancel out all the terms that can be canceled. And we find out that sigma 2 equals sigma 1 divided by n. So the smaller sphere gets a greater charge density. Charge will then cluster on sharp points. In other words, things with smaller radii. Now we're going to find the electric field ratio. E2 over E1 equals KQ2 divided by R2 squared divided by KQ1 divided by R1 squared. And this ends up being 1 over n. So E1 equals NE2. The smaller sphere has a greater electric field. So electric field lines bunch up at sharp points. Those are smaller radii. Which group of charges took more work to bring together from a very large initial distance apart? This group or this group? Now, what you want to do is you want to remember to sum up the energies for each pair of particles in the grouping. All right, so here we go. Case 1, it will be K times 2Q times Q divided by D. Case 2, U equals 3 times K. There's 3 charges here. KQ, Q divided by D. And case 2 is greater than case 1. So case 2 is the correct answer there. What is the electric potential at point A? Here's a charge of minus 50 microcoulombs over here, 26 centimeters on the positive x-axis. A Q2 of positive microcoulombs is 26 centimeters on the negative axis. Okay, so what is the electric potential at point A? Well, it's closer to Q2, so it's going to be positive. It'll be greater than 0. So the two charges are equal magnitude and opposite sign. Point A is close to the positive charge. The potential there is greater than 0. Okay, what is the potential at point B? Well, point B happens to be equidistant from the two charges that are equal and opposite. So the potential there should be 0. Now, the electric field there won't be 0, but the potential will be 0. 4 charges are arranged at the corners of the square. Find the electric field E and the potential V at the center of the square. In which is the direction of the electric field at the center of the square? Okay, well, you look at the positive and negative charges here. The electric field is going to begin on positive charges and go toward negative charges, and ditto for here. So the electric field, if you look at that, we got one vector is going this way, the other vector is going that way. The sum of them is going to be to the left. So that's the electric field. Now, if you look at the potential, you can kind of see that these are all equidistant from each other, and there are 2 negative charges and 2 positive charges, so V equals 0. Now, you can have a potential being equal to 0 and the electric field not be equal to 0. So in this case, the correct answer to this one is the E is not equal to 0 and V equals 0. The scalar contributions from the 2 positive charges cancel the 2 minus charges. However, the contributions from the electric field add as vectors, and they do not cancel. So E is non-zero. The E field would point to the left. Which of the following statements concerning electrostatic situations is false? No work is required to move a charge along an equipotential surface. That's actually true. You don't require work to move a charge along an equipotential surface. If the electric potential in a region of space is 0, should say within a region of space is 0 volts. The electric field within that region must also be 0 volts. Okay, this one is false because you can have an electric potential be 0. Here's a parallel plate capacitor, positive 10 volts, negative 10 volts. The electric field is definitely not 0. The potential in the center is 0. If a charge is moved along an equipotential surface, there is no component of the force acting along the charge's path. That one's true. The electric field is always perpendicular to the equipotential surfaces. That's always true. The electric field is 0 volts per meter and everywhere inside a conductor. That's true. So the false one is B. And also we got to remember the value of the potential is set by choice of reference point. In the system shown in the drawing, a positive charge Q is placed at the center of a hollow conductor that was initially electrically neutral. The arrows are pointing to 4 locations. Number 1 is a point inside the conductor near the outer surface. Number 2 is a point in the hollow space located halfway between charge Q and the inner surface. 3 is a point in the conductor halfway between the inner and outer surface. And 4 is a point in the conductor near the inner surface. Which of the following choices best ranks the electric potentials at the 4 locations? Well, the electric potential point 2 is going to be the highest because it's closest to the charge, and charge is positive in there. All the rest of these are going to be on equal potential surfaces. So 2 is going to be greater than all the rest of them, and that should be B. Okay, pretty much the same question, but now which of the following choices best ranks the magnitude of the electric fields at these locations? Okay, so Q is going to be a positive charge, so it's going to have an electric field. Okay, inside of here, there will be an electric field. However, inside an equipotential surface, there is no electric field. So in other words, 2 will be greater, and then the rest of these will all be 0. So that's B. The electric potential of an uncharged spherical conductor with a radius of 0.1 meter is 10 volts. If the sphere is located in a region of space with no electric fields, that is E equals 0, what is the electric potential at 0.2 meters from the center of the sphere? Well, if the electric field is 0, that means it's an equipotential surface. That means it'll be everything's at the same potential, and that would be 10 volts. A good example of this is the spherical conductor is in a conducting fluid. Everything is a conductor and an equipotential surface. The electric field inside the conductor is 0, and everything's at a potential 10 volts. Now remember, potential is set by the choice of reference point. You can set it to anything that's convenient. Thank you.